All right, there's some midterms up here. Come pick up yours if you haven't so far. As Nathan emailed, the median and the average were both around 112, 114, something like that, out of 140. So people did reasonably well. If you got a lot below that, you got some work to do. You've underestimated the material. Any questions about the midterm? If there's any grading issues, please see Nathan first, and if necessary, see me afterwards. So last time we left off with Turing machines. We said a Turing machine is simply a finite automata. Yeah. Well, he's asking, is there a curve for the midterm? It's a grading scheme that we talked about at the beginning. The midterm is worth a certain amount. If you do extra credit, that counts for a lot. Attendance counts for a bunch also, just for showing up. You get quite a bit of percentage points. In fact, the attendance roll is circulating today. We're taking attendance. And if you do even more extra credit, you can get above and beyond the extra credit percentage that I promised. So even if you kind of really messed up on the midterm, you can still get an A easily. Just do a lot of extra credit. And you have many weeks to do it before the semester is over. So I'm all about second chances or even third chances, but you got to work with me, right? If you got to this point and you're still not sure what a subset is, or if you think a subset of a regular language must be regular, you're way off. You completely underestimated the task, of learning this material. If you haven't solved lots of problems, like I kept asking you to do all along, again, you've underestimated what you need to do to get a good understanding of this set of abstractions and ideas that I keep harping on. So maybe for some of you, the midterm is a reality check. But it's not too late, right? With TAs, there's office hours almost every day for TAs. There's Monday night sessions. There's all sorts of help. There's the book. You can look up stuff on Wikipedia. There's even lectures. I'm recording the lectures. It's all on Collab, right, including this one. So, but you can't just learn it just from looking at the slides only. It's like saying, I know how to play basketball really well because I watch it every weekend on TV. This is not a spectator sport, learning. You got to do it. You got to practice it. You got to solve problems. Problem solving, you got to participate in. It's not a spectator sport. Okay, and for some of you, maybe you're beginning to get that. That's okay. It's part of your learning experience. Any other questions? All right. So a Turing machine is a finite automata with a tape. This works like a finite automata, except you can also read and write from a tape. And the read-write head only can look at one square at a time, move left or right, very myopically, very locally. And from that, we can do everything. That was one of Turing's many contributions to humanity. He showed us that arbitrary computations, however complex, whatever we can think of as computable is doable by a Turing machine. In fact, that's called the Church Turing thesis. We'll get to that. Okay, so then we said, well, what about enhancements of Turing machines? What if we use a larger alphabet? And then we showed, no, using a larger alphabet doesn't get you anything extra, maybe a little bit of efficiency, but that's it. It doesn't make some impossible things all of a sudden possible just because you have a larger alphabet, because you can encode a larger alphabet with a smaller alphabet of just 2 characters. And in fact, your computers that are in front of you or in your pockets and purses do that all the time, right? It's called ASCII or EBCDIC or Unicode or whatever the encoding scheme is for larger alphabets using smaller alphabets. We said, okay, what if you have a double-sided infinite tape? We said, okay, that doesn't buy you any superpower either, because you can take it, dovetail it along with the other half of the tape that you had before, and now you have still a single-sided infinite tape that has a beginning. The double-sided infinite tape has no beginning. You're just starting somewhere, but it can go in either direction forever. So double-sided tape, same as one-sided tape. Just remember to hop every other one when you're on one side and do the evens versus the odds. Keep track of the parity, you can easily do that using some of your states as you compute. It's easy to do. It's a form of dovetailing. It's a simulation. And double-sided infinite tape doesn't buy you extra anything, except maybe efficiency. But here, we're not talking about efficiency. We're just talking about what's possible, efficiently or inefficiently, as long as it's possible or impossible. That's the point so far. Later, we talk about efficiency. That's a lot more convoluted and subtle when we get to NP-completeness, for example. All right, if you have multiple read-write heads on the tape, we said, again, no big deal. Just simulate the read-write heads using capital characters to denote that there's a tape head there on that square, along with a character that's part of the data of that square. And use different colors, which means, yet again, different characters, more characters. We already know how to simulate more characters with only 2 characters. So you can simulate all these read-write heads using a single read-write head and a larger alphabet. How many get all this so far? All of it? OK. Any questions about any of it? It's all simulations. OK. Doing things by means of other ways of doing it. But the point is, it's doable. It's not an impossible task. So as one of the heads move over here, you got to go, change that, go back, and do that for every single motion of these 3 heads. A lot of work. It's tedious for the machine. But machines don't mind tedious tasks. Think about it. If the machine complained when it asked it to do repetitious, tedious things and kept insisting on its rights and maybe go on strike, we would all be in trouble. So tedious but doable for the machine. And doable for us in programming these machines as well. So if you have multiple tapes, just like multiple heads, you can dovetail them all together, right? And keep track of everything. And so multiple tapes doesn't do you any good. 2-dimensional tapes, we said that you can take all the rows and, again, kind of mash them together, zip them together, or dovetail them together. Separate them so you don't get confused when one row starts and one row ends. Implicitly, the rest of every row past the last non-blank character are all blank characters, so you don't have to represent those explicitly. If I say a trillion blanks, I just said it very quickly. I didn't have to say it a trillion times for you. There's a couple of tricks here. If you go left or right, you're good. If you go up and down, you got to jump a whole lot to the next section and keep track of where you were by marking things and doing all that bookkeeping. Again, tedious, but doable. How many get that part? You got to do a lot of marking to jump from the red to the blue, from the blue to the green region, and so on. That's OK. You just mark things as you go, leave breadcrumbs as you go, which means mark the characters, which means use more characters, bigger alphabet. But we already know that using bigger alphabet doesn't buy you anything extra. You could always do that. In fact, that's how compilers implement the 2-dimensional arrays. It's called row major order. Non-determinism, that's where we stopped last time. So if computer is non-deterministic, a Turing machine basically can do several things in the next step. Like, for example, it's right there, and in the next step, it goes to the right one. If it's right there, in the next step, it overwrites that with another character and goes to the left instead of to the right, bifurcating the computation, non-deterministically choosing both paths. You have 2 different computations now, bifurcated. It's like 2 different threads on your computer. It's like forking a shell in Unix if you're a Unix aficionado. So basically, the Turing machine parallel simulates both of these threads by, again, just like before, putting them on the single tape together with marking where each read-write head is, blue and red, by marking that character using color, which means bigger alphabet with more characters yet. And then simulate both of these in parallel, which means when this machine, again, each one of these does its own next step. This one happens here, this one happens there, independently of the other. The read-write head of this bigger simulating machine has to take care of the first red simulation and take care of the blue simulation separately, independently in sequence. But you're essentially doing a parallel simulation of 2 threads, or rather a serial simulation of 2 parallel threads. Let me get the semantics right here. And let's say one of them, like the blue one, now bifurcates into 3 more. That could happen. What do you do next? Take a wild guess. It's pretty straightforward. Yeah, copy this blue 3 more times here, and in each one do each one of the 3 respectively. It could be all 3 different than one another. And then now we have 5 things to simulate. this, and whatever its children are. Well, I guess if its children are being simulated, you don't need to simulate it anymore. Now it's just children instead of it. So one of them can overwrite the blue eventually. And then you just keep going. So simulating a non-deterministic computation can be easily done with a deterministic machine. This whole simulation here is deterministic. There's no ambiguity about it. There's no multiple next states. It's brute force, step-by-step, deterministic simulation of a non-deterministic bifurcating computation. How many get this? All right, that's not enough. Ask me questions. Only 10 people out of, 100 plus, 130 even. So ask me questions about this. Yeah. This one? Yeah, so basically you copy, so it bifurcates in two directions. And the simulator knows that it does because the state says, I'm going 2 places now. So it says, okay, wait a second. Before you do that, let me copy you 2 times here. And if you want to go in 2 places, fine. I'll go into one direction here on that copy, do the appropriate thing. Go in the other direction on that copy, do the appropriate thing there. Now I got 2 copies of you, which are your next 2 states, you being the non-deterministic computer, and I'm being the simulator, the deterministic simulator that's simulating you. I'm basically following all the paths for you the hard way, recording tediously what you would have done in every single path that you chose to go down as a non-deterministic computation. How many get it now? All right, we picked up a few more people. I see a lot of people that are still kind of staring at me blankly. Ask me questions. What do you want me to repeat more of all this stuff that's going on this slide? How many understand what a non-deterministic computation is? Let me know. Okay, good. That's a bunch. We covered that many times in finite automata and push automata. You had a question? Yeah. For a Turing machine? No. For a finite automata? Sure. For a push-down automata? Yes. For a Turing machine? No. Why not? Why doesn't have it? Why not 2 heads make it more powerful? That's right here. Right? Why not? Because you can simulate with a single head. For a Turing machine, you can. For finite automata, 2 heads are better than 1. They're a superpower. What language can you recognize with a finite automata with 2 heads that you cannot do with 1 head? Give me an example and do it in 2 seconds. 0 to the n, 1 to the n. Good. What language that's not context-free could you recognize with a push-down automata with 2 heads? Whereas a 1-headed push-down automata could only recognize context-free languages. 2 seconds go. Yeah, 0 to the n, 1 to the n, 2 to the n. How many get that? Good. You see, you get a lot of mileage out of these 2 languages, 0 to the n, 1 to the n, and 0 to the n, 1 to the n, 2 to the n. There are typical languages that are good for counterexamples. Here, if you have 2 heads, no big deal. You can simulate it with a single head by going back and forth and marking things. And I'm not saying it'll be fun or quick. It'll be tedious and boring. But the point is, it's possible. The other cases we just went over are impossible. A finite automata cannot possibly recognize 0 to the n, 1 to the n. It's an impossible task for a finite automata. It's not just hard or inefficient. It ain't going to happen. We already proved that. In one word, what was the proof technique? What was the proof technique in one word that a finite automata cannot recognize 0 to the n, 1 to the n? You can buy a vowel if you want. Yeah. Pumping. How many get that? Pumping. Yeah, good. Now you're getting the hang of it. Right? Be agile with these concepts. And that comes with a lot of practice. There's no 2 ways around that. All right, so that's multiple heads, multiple tapes, 2-dimensional tapes, and we just covered non-determinism. Any more questions about non-determinism? Yeah. What's that? Why does it have to go in 2 different directions? It doesn't have to. It's just what the non-deterministic does in this example. If it went in one direction, fine. Then still have 2 copies, and they'll both be going in one direction. But the point is, whenever it's like, let's say a program had parallelism in it. Some programming languages support parallelism. How many understand or know that or seen that? Okay. So if you have a parallel execution all of a sudden in a program you could say, go here, but also go there, simultaneously in parallel. Well, what does that mean? It means the compiler, or the operating system, I guess, makes a copy of that entire program while it's running, copying its entire state, all the variable values and all the arrays that it's created. So it just makes a complete copy of that program, complete image copy of that program. And one copy is going left, and another copy is going right. How many understand that, how you'd implement parallelism like that? Okay, so that's exactly what we're doing here. So what a compiler would do to support a programming language that has parallel constructs. Yeah, up there. You make a copy of the entire tape on the next bunch of tape. That's all. Just like in the compiler case, you take whatever was in the memory so far for that program or that thread, you make a complete copy of that, verbatim copy, over there in the next chunk of memory. Because you always have more tape. And by the way, let's not take it for granted. How do you make a copy of the red here in the blue? It's not going to just appear like that. You can't say blue is equal to red. That's not an instruction on a Turing machine. Remember what a Turing machine can do? Change states, move its head left or right, recognize a character, change a character on a tape one at a time. It's tedious. So how do you get the red to be copied over to the blue? Verbatim. It's not a trick question. It's easy, but you got to say something. Silence is not an answer here. It rarely is. So how do you copy? Let's say only the red is there. The red is what this is. 110101. Okay. All of a sudden it bifurcates here and here, so you got to make the red copied over to the blue that wasn't there before, and then simulate separately the red and the blue going forward independently of each other like two parallel threads. So how do you copy the red to the blue? It's not hard, but you got to say something. Yeah. Yeah. First, go to the end of the red. Put a $sign there. By that I mean a separate character than any of the characters in the red, so you know where the red ends. Okay. Now go back to the beginning of the red. That is one after the first unmarked character after the first $sign. See if it's a 1 or a 0. Remember that in your finite control. Then find the $sign again by going all the way to the $sign. Then writing that 1 there, that's the same as the 1 here. So that 1 becomes a 1. Now go back, skip over the $sign, skip over all the other characters. Go back to the next character, this one. Remember what it is. Find the $sign again. Skip over all the blue characters again, and then put that 1 there, copy it there, then reset, copy the 0 here, and the 1 here, and the 0 here, and the 1 here, and go back and forth, and copy, until you get the red copies to the blue. One tedious scan at a time per character. I told you it's not going to be fun or interesting or efficient, but the point is it works. And it doesn't have to work. An algorithm for the halting problem doesn't work and can't work now or ever by us or by any omniscient entity. It doesn't exist like the integer between a quarter and a third doesn't exist. Finding the integer between a quarter and a third is not just difficult. It's not just inefficient. It ain't there to be found. It's worse. Okay? And here we're saying it's not that bad. It's just inefficient. You can do it, and this is how it's done. And by the way, when you take this one and write it here, and you take this one and write it there, when you go back, how do you know where you left off? How do you can't go all the way back to the $sign because, maybe you at this point in the process, you've copied all 17 characters in red to here, and there's another 100. So how do you know to go back to the 18th character, not the first? And how do you accomplish that? You don't have a counter somewhere that you can count to 17. You're right. You got to somehow keep track of it. How do you keep track of it? Without a counter. How many understand my question? It's a technical in-the-weeds question, right? It's the assembly code of Turing machines. Mark, Thank you. One word suffices. Mark where you've been. So mark this one, and then mark this one, and then find the first marked one, and the next one will be unmarked. You skip over the unmarked characters, you find the marked character, you go one to the right, and that's your next character, and mark that too. Now, somebody else besides him explain what does marking mean, really. When he says marking, what does it mean in terms of states, characters, tape, read, write? Yeah. Yeah, rewrite that one as a one dot, as a capital one, or as a purple one instead of a red one. And what does purple one mean instead of a red one? It means a larger alphabet now. Now the alphabet has 0, 1 in red, 0, 1 in purple, and maybe a couple other colors for 0, 1. That's okay. We already know how to handle larger alphabets with simple alphabets of only 2 characters. So that doesn't cost us anything extra in terms of a superpower. Right? We're not making a human fly here. We're just making a human walk a little faster. It's doable. We're not asking the machine to do anything impossible. Yeah. Yeah. And when you mark it, it'll become a purple one. And you find the first red one, not a purple one, when you scan back to find the next character to copy over. So you skip over red characters, you find the first purple character, and then you know that the one to the right of that is the next character you got to copy. And when you copy that, you make that purple too. So next time, you will skip over that and hit the next one and the next one and the next one. Does that make sense? Yeah. Well, so first, let's say you have a purple number one and a purple number and a red number one and a blue number one and maybe whatever other colors you need, a finite number of colors. I think purple, blue, and red will suffice. What it means is just another character in the alphabet. So now let's assume that the alphabet of this simulator now is not just 0, 1. It's red 0, red 1, blue 0, blue 1, purple 0, purple 1. So now the simulator has 6 characters. That's okay. It's not a million, and it's not a Google, and it's not infinite. It's 6. And that'll carry it through the entire simulation. And as it marks back and forth, it changes them into purple, so it knows where to pick up the copying where it left off the last time. It's the boundary between the blues and the purples. And then one more blue becomes purple, and that's where the next copy will start from the next scan around. Does that make sense? And when you finish copying all these reds to the blues, go back and unpurple the marks. Make them blue again to get ready for the next set of passes of simulation. Does that make sense? No, they're always in the alphabet. I'm creating the simulator. I get to choose its alphabet. So I choose the alphabet to be 6 things. Red 0 and 1, blue 0 and 1, and purple 0 and 1. Now I can then merrily simulate this just the way I described, right? So I'm the simulator. I'm creating the simulator. I'm showing you how the simulator would work. I get to choose how the simulator operates. I get to choose its alphabet, its state set, its transition function, and I'm describing how it works. So yeah, it can have as many characters in the alphabet that I want. I'm writing it. I'm constructing it to do that job, right? Question? Yeah, let's be a little bit careful. Let's not say the tape is infinitely long. It's a bit of a, the tape could be arbitrarily long. When you use the word infinite, I get nervous because I'm not sure if you realize what you're saying. I'm being a little bit extra pedantic here because so you don't get a misconception about what's going on. The tape is not infinite. It could be extended arbitrarily to the right. But at any point in the computation, only a finite number of tape cells contain something other than blank. Does that make sense? That's not quite the same as saying it's infinite, Maybe I gave you too precise of a definition, and that may be throwing you off. But if you say it's infinite and rush on, later you may get the misconception that this simulator has to do an infinite number of things. No, it doesn't. It doesn't have to do an infinite number of things. Only a finite section of the tape is occupied by characters at any given moment. The rest are all blank, and if they're all blank, they might as well not be there. So you can think about this so-called infinite tape as a finite tape. It could be extended arbitrarily to larger and larger lengths, but that's not the same as it truly being infinite. It's potentially arbitrarily large. Let's take an example from the integers. There's integers that are arbitrarily large. For every integer, there's an integer larger than it, but there are no infinite integers. No integer is infinite. Infinity is not an integer. How many get that? Infinity is not an integer. Good. And you can easily prove that. I'll leave it up to you to construct a proof that infinity is not an integer. Question? All right. So okay, with that, go ahead and finish the question. Just don't use the word infinite. Yes, I like that. Use the word infinite again just now. I asked you not to use it. Yes, I like that much better. No. That's a very good. So he's saying, why doesn't it get you more and more and more colors? I wrote this here in red to denote that it's this thread of the computation. I wrote this here in blue to denote that it's this blue thread of the computation. I color-coded them for you, so you know which is which. But they're both black. Does that make sense? Yeah. So it's not really blue and red. It's the same color. I just denoted them as separate colors, so you know which is which. So you know that this one went here and this one went there. So you keep track of this business. Get ready for it, get ready for it. Bam. So you know which one came from which. That's why I color-coded them. They're really the same color. They're all black. The purple that I mentioned is different than these zeros and ones. And it doesn't have to be purple. It could be green. I mean, I'm just using a label, right? I'm just saying it's a separate character. Just like that dollar sign is a separate character than the zeros and the ones. Where did the dollar sign come from? This one didn't have dollar signs. This one didn't have dollar signs, but I have dollar signs here. Because I'm the simulator. I'm building the simulator. I can throw in whatever characters I want, and there's a finite number of them. If there was an infinite number of them or an unbounded number, I'd be in trouble. You're right. That's going to get out of hand, and something will go awry. But I just need the original characters, zeros and ones, which are these. I need a dollar sign to separate stuff, so I know where one segment begins and the other segment ends, and so on. And I need a couple other characters to mark things, to mark a 0 or mark a 1. So I call them purple 1, purple 0. They're really just two more characters. If you want to use monetary signs, I call them yen and pound, or euro and peso, whatever. There's little symbols for all of those. Make sense? But you're right, there's no unbounded number of characters. Otherwise, something would be way off here. And if one of those wants to bifurcate into two more, again, make a copy of it. How? The hard way. Mark, copy, go back, mark, copy, go back, find the unmarked one, go back, copy, scan back and forth, make the copy. Then make another copy if you have to, and so on. And then simulate all of those in parallel for each time step of this parallel machine, this non-deterministic machine. This will simulate each and every block, which are now parallel, separate, independent, simultaneous threads going on. But I'm simulating them serially, not in parallel, sequentially, not non-deterministically. In fact, on your computer, apps or programs can sometimes create threads. How many get that? Threads, how many work with threads in those parallel processes? Your computer doesn't really have parallelism at the hardware level. It's one microprocessor. And some microprocessors have several cores, but let's leave that alone for now. Let's say this is one microprocessor. How can you run 20 threads on one microprocessor? Don't you need 20 microprocessors to run 20 threads? Yeah, you keep going back and forth, round robin, the time of the processor, the processing power among all the different threads, time slice the work of the processor among all the threads, giving them 1 millisecond at a time. And to you, it looks like it's all happening at once, but that's an illusion. It's really happening serially. The microprocessor is just multitasking. Just like you multitask in your daily life. You can cook while you're on the phone. You're not really doing it in parallel if you think about it. When you say a word, you're not really thinking about stirring the pot. When you stir the pot, you kind of maybe miss a word. But you go back and forth enough so that, it looks like you're doing it together. Some of you may try to multitask while you're driving by texting. That's not really parallel either. It's serial, whether you realize it or not. And occasionally, you'll give one of the two tasks too big of a time slice, and the other will starve for time. And that's called a car accident. How many understand that example? Good. Any questions? That's exactly what this is doing. This is time slicing between all these threads serially, one at a time, giving each one some attention at a time, and together it looks like they're all happening at once. And it's doing it serially, not parallelized. So the point is, parallelism doesn't buy you anything extra. Whatever you can do in parallel, you can also do serially by time slicing and time sharing the processor across all of them round-robin fashion. That's all we're saying here, really. You're all doing it in your daily lives already. Just don't do it while you're driving. That's dangerous. And the reason you have an accident while you're texting and driving is because it's not really in parallel that you're doing it. You're doing it serially, whether you realize it or not. So when you do one, you neglect the other, just like this does. When it's processing the red, the blue is not doing anything. Then when processing the blue next, the red is not doing anything. But if it's doing it fast enough, it looks like all of them are moving forward together. Any other question? How many get it now? Oh, good. We picked up a bunch of people. Excellent. I'm doing my job then. Yeah. Yeah, so there's another couple of characters that we need. Now we know how to mark things to get it, across as a copy. You need to also mark where the read-write head of this parallel machine is on this segment. So this character here, where the arrow is and the box around is different. That one is like read-write head 1 as opposed to just a plain 1. And same for right here. That's a read-write head 1 as opposed to just a plain 1. And you still need a couple for the 0, a read-write head mark for the 0. And as you go and you try to simulate it, you go to find that marked one with a box, and then whatever this transition function will do next is what this simulation will do next here. So if this wants to now go to the left, this will go to the left, unmark this with a box, mark this with a box, and perhaps even change that 1 to a 0 if that's what this transition function here for the parallel machine would have wanted to do. You just basically blindly, pedantically follow the simulated machine as you're simulating it. Whatever it wants to do, you do as well as a simulator. So yeah, you need a couple of extra characters to denote where the read-write head is on top of the character that's already on the tape. So that when you go, you know where to move from the read-write head either to the left or to the right, just like this simulated machine wants to do. Yeah. Yeah. Yeah, so allow me to illustrate with an example. Let's say I have these 4 tape cells. These are your exams, by the way. I'm not going to mutilate them or anything, but I want to copy these 4 over there. So I can't just take all these 4 and put them here, because I have nowhere in memory to put 4. I can only hold 1 at a time. So I go and look at the first one. I'm going to copy it over there, but before I do, I'm going to mark it. Everybody get that? I moved that pile forward. That's a mark. Now we're going to take this, put it here. So I copy that first one. And I'm going to then go back all the way to the beginning. I'm the simulator. I'm going to find the first unmarked one. Well, this one is marked because it's moved. This is the next one. Okay, good. I'm going to take this, mark it. Go over here, find the first blank symbol, put it there. Repeat. Go back to the beginning. This is tedious, but it's happening, right? It's not impossible. This one is marked. Okay. Look at this one. This one is marked. Fine. This one is not marked. Mark it. Take this, walk all the way to the first blank here, copy it. One at a time. Go back to the beginning. It's kind of fun, actually. Not too bad. Marked. Okay. Marked. Fine. Marked. Fine. Unmarked. Okay. Mark it. Copy it. Find the first blank. Place. Skip over all of those. Okay. Go back. Marked, 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 marked. Nothing else? Good, I'm done. Go back to the beginning. Mission accomplished. Block copied. How many get it now? Oh, good. Well, if that's what it took, I'll do this every time. Whatever it takes. I'm here for you. Any other questions? That's what the Turing machine does. It does it the hard way. The point is, it's not impossible. It's just tedious. Okay, now I have two copies of this. And one of them is the read-write head, whatever has the read-write head character on it. Now I got to simulate this and this for one step each. So if the red one wants to do something to this, like mark this with something and then move the read-write head to here, I do this. Then I go over here, find the read-write head here. Let's say it's over here. Then one goes to move to the right. So I move to the right, and now the read-write head is here on this one. Now I've simulated both blocks one step forward. If one of them wants to bifurcate again two ways, I'm going to have to copy that. I won't do that right now. I hope you forgive me. And then, again, simulate each block separately, one step forward, independent of the other blocks. And so it goes forward. Yeah. You don't have to. He's asking, can you dynamically create another Turing machine using a Turing machine? Let me ask you something about your programming environment. If your program wants to bifurcate and create another thread, does your computer have to create another computer right beside it with all the plastic and metal and silicon that entails? Well, he's asking, is it possible, I guess, as opposed to necessary. So definitely it's not necessary. Whether it's possible, it depends on your level of conceptualization or abstraction. To keep it simple, let's say no, it's not possible. A Turing machine cannot create another Turing machine. It's not what a Turing machine can do. Just like a Turing machine cannot make a phone call or text you. Does that make sense? It's not that it's an impossible task for a machine if it was programmed the right way and abstracted and conceived of the right way, because all your Turing machines implemented in silicon and plastic and metal and on your desktops right now and in your pockets and purses, those can text, right? And those can make phone calls, and those can open a website on a browser. So why can't a Turing machine do that? Well, conceptually it can if it had the right peripherals. So can a Turing machine create another Turing machine? Let me now answer it more abstractly. So first I said no, it can't. Now let me answer it more abstractly and answer it in the opposite way, saying yes, it can. Just like your computer can. Can your computer create another computer sitting right next to it? And both will now work on two different parallel threads. Technically, yes, it can. If it had a fancy 3D printer that works in metal and silicon, and it's connected as a peripheral to that computer, and he knows how to operate this thing, and a 3D printer was sophisticated enough that he can print a whole new computer from scratch, and soon we'll be able to do that with 3D printing. Yes, your computer can create a copy of itself sitting right next to it with the right raw materials and 3D printer appropriately. And now we have two computers, and now they can both do, and each one of those can create more copies of themselves But you have to be careful because that's what happened in the movie Terminator. Machines created more copies of themselves and they did some bad things. And humans weren't too happy about it. Yeah. Yeah. So you don't copy the transitions. You copy the block of tape from here to there, and on it, you enact the transitions. You execute the transitions on these blocks. Yeah. Okay, so you're using the word creates in a funky way. You know, you're overloading it with semantics that aren't really on the table. So in the simulation I described, all you're doing is copying a block of tape, and you're applying the same transition function from above to each block individually. The transition function isn't being copied. The Turing machine isn't being copied. Just like in a regular programming environment, like on your laptop, when you create two parallel threads, you're not copying the computer. You're not copying the operating system. You're not copying the compiler. All you're doing is copying the memory block from here to here, and you execute the exact same program as before, that single copy of the program, on both blocks in parallel independently of each other. There's only still one computer and one compiler and one operating system. You're not copying those. So be careful about semantics. You know, it's a little dangerous to just throw words around as if they're nothing. Some people don't mind, and some of them get elected to office. But you know, I digress. You know, be careful what words you use. You know, when you say copy the Turing machine, think about what does that mean to copy the Turing machine, and whether it's even necessary here. You're not technically copying the Turing machine. You're copying the tape of that Turing machine, and you keep simulating it as the original Turing machine would have. But you're not copying the machine itself. Does that make sense? Just like you wouldn't be copying your compiler and operating system every time you open a new thread on your machine. You're just copying memory, basically, not the other stuff. Okay, I think we beat that horse to the ground. Let's see what we got here. What if you have combinations? What if you have a complicated combination? Let's say you have a Turing machine that has a two-dimensional tape. It's infinite to the left and also infinite, or infinite to the right and infinite up, two-dimensional tape. And it has several heads on that tape independently of each other, all moving simultaneously independently of each other. And it has a second tape, and that tape is one-dimensional, but it's two-way infinite. And it has a strange new alphabet on it. This one is Greek. Anybody know Greek enough to read this? What does it say? Get back to me on that. And what if it's also non-deterministic? Okay. And so it's enhanced in several different ways. It's non-deterministic. It has two different tapes, several heads per tape, different alphabets on different tapes. One of them is even two-dimensional, and you can even pile on other things. So it combines all of these enhancements that we saw before. Multiple tapes, multiple heads, larger alphabets, different alphabets, and non-determinism on top of everything else. Does this machine have any superpower? Is it Superman or is it Clark Kent? Can it do anything that ordinary mortal machines cannot do? Exactly. You can simulate all of these things separately. How many can see that coming? All right. Why is that? Well, take them one at a time. All these enhancements here that we saw earlier, all these simulations are completely orthogonal to one another. They're independent of one another. You can compose them any which way you want. So take this complicated machine that we just saw, and basically, first of all, flatten out this two-dimensional tape into a one-dimensional tape using row major order. So now you have two one-dimensional tape. Then take these two-sided infinite tape, make it one-sided by folding it on itself. Now you have two one-sided infinite tapes, one-dimensional infinite tapes. That's the next transform. On top of that, then combine these two tapes by dovetailing. Now you have one-sided semi-infinite tape. Then represent all these larger alphabets with smaller alphabets, such as 0 and 1. That's the first enhancement that we saw, is alphabet encoding. Then get rid of the non-determinism by this parallel simulation business that we saw on this previous slide here. And at the end, you'll have a one tape, one head, alphabet 0, 1, deterministic, not deterministic, but deterministic Turing machine doing the exact same job as this complicated one does, only it's a lot simpler machine. Try to say that one 3 times fast. How many get this? Any questions about that? In other words, you're composing these simulations or this transformation on top of each other, each one simplifying the machine, removing heads, removing tapes, flattening tapes to 1 dimensions, getting rid of non-determinism, making larger alphabets smaller, blah, blah, blah. By the time you end up with a single machine that's deterministic, has alphabet of just 0, 1, one head, one tape, one-dimensional tape, not 2, and end of story. Okay? So the point is, not only did I show you a lot of enhancements that can be simulated if you didn't have these enhancements, but if you had combinations of these enhancements, same deal. Combinations aren't any more magical than one at a time, because you can apply these transformations one at a time, getting rid of all these enhancements one at a time until you have no more enhancements. Your machine is no longer on steroids. It's average and normal. Okay? So, and people have tried all sorts of other enhancements. I just showed you half a dozen different enhancements, more heads, more tapes, high-dimensional tapes, non-determinism, larger alphabets, whatever, and combination. But there's probably dozens more that are conceivable, and people have tried, since Turing proposed this model, to increase the power of this model by all sorts of fancy enhancements. They failed, which means this model is very, very powerful. If the model cannot be improved at all, cannot be made any more powerful in terms of what it can recognize, what languages it can recognize, it's a pretty powerful model. In fact, to this day, it's the most powerful model we can think of, a Turing machine. With one head, one tape, alphabet character, 2 characters, deterministic, not non-deterministic. So that simple model captures everything we as a species can conceive of trying to compute. Anything. Whether it's adding 2 numbers together or playing World of Warcraft and everything in between. A Turing machine could do all of it. We know of no more powerful machine model than that. And that's saying a lot, because Alan Turing created this in 1936, almost a century ago, and it's a pretty simple machine. A set of states, a transition function. It's basically a finite automata with a tape. That's all it is. All it is in quotes, because it can do everything we can conceive of as doable, which is saying a lot, because look at all the things we've done so far. Right? We created this building. We created planes that fly. We created other machines that work and think and do stuff and enable us to perform all these almost magical things. They're all Turing machines. Any other questions so far? That's how dramatically powerful that model is. Try as we might, we can't possibly come up with any better, more powerful model than that. With finite automata, we could. Finite automata, it's easy to enhance into a superpower. How, for example? What's the superpower for finite automata? What do you have to do to it? Something very simple to make it more powerful. All of a sudden, it can do things that it couldn't do before. Add a stack. Or, that'll do it, but what else? Separate superpower. It's not a hard question. Add an extra head. Or a few other things. But here, not so much. All right, let's talk about recognizing versus deciding. So if you have a Turing machine that accepts by halting, that's good, and reject by halting also, but in either case it halts and either rejects or accepts. But it halts in either case, like a program would. Let's say you have a program, you give it something, and it tells you yes or no, like it's a prime or it's not a prime, or it's a dog or versus a cat image, or some third option. But it always halts and gives you the answer, as opposed to running forever. Because if it runs forever, not only doesn't it give you the right answer, it doesn't give you any answer, not even a wrong one, because it's running forever. It's not giving you any answer. It's just running and running and running, and you're just waiting and waiting and waiting. So running forever is not so good. So ideally, you want a machine or a program to never go into an infinite loop. Of course, don't get me wrong. Occasionally, there's a rare exception, and occasionally you want the program to be in an infinite loop, and if it ever stops running, that's an error condition. Give me an example of that. 2 words. Operating system. How many see that? Okay. An operating system, you don't want it to halt. If it halts, it's called a crash. So, but in most cases, you don't want it to run forever. You want it to stop and produce some answer. Okay? And so, a language is called Turing decidable, or just decidable for short, because that's supposed to be Turing machine decidable. It would be C++ decidable, or Python decidable, or Pascal decidable, whatever your favorite language is. But it's called decidable if that language is called decidable if it's exactly the set of strings that are accepted by that Turing machine or that program or whatever the mechanism is that accepts or rejects strings. So if that thing, say a Turing machine, always halts, the strings that it halts with a yes is of course a language, and it's called a decidable language because that machine decides that language. You give it one of those strings that it halts on, it says yes. Give it one of the strings that it halts on and rejects, it says no, and all the yeses are the language by definition. Right? The yeses are all the strings that it accepts, so the language of a machine is all the strings that it accepts, all the strings that it says yes on, or ends up in an accepting state when it starts running on each one of those strings separately. All right, so it's a definition. Turing decidable is a language that is exactly the set of strings that Turing machine halts and says yes on. And it's an if and only if. So if the string is not in a language, it can't run forever. It must also halt, but say no. Either way, it's got to give you an answer on every single string of the language. So that makes the language decidable. It's a definition. Soon we'll see, very quickly, we'll see theorems that fall out of the definition, non-trivial theorems too. So for example, let's say the strings are A, B, A, B. So sigma star is up here. Sigma star is all strings over the alphabet. In this case, it's A and B, the alphabet. And all these strings, here it's indicated for each string whether it accepts or rejects. So check mark in green means accept. X in red means reject. But either way, it says yes, no, yes, no, 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 yes, no, 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 yes. So what's the language accepted by a machine that has this kind of behavior of yeses and nos? In one sentence or one phrase, what's its language? Just from this example, looking at it. It's A star. So it's a regular language, particularly it's A star. So A star, therefore, is a regular language. And it's also a decidable language because there's a simple Turing machine or algorithm or piece of code that recognizes strings in A star and says yes on them. And if a string not in A star comes along, it recognizes that as a non-string in A star, and it says no for that string. And it's very easy to construct an algorithm or a Turing machine that does that. Just checks that all the input characters are A's and nothing else. How many get that? So it's a definition and an example of that definition. All right. So again, we emphasize that the machine must always halt no matter whether the string is in or out. It must always halt and tell us whether it's in or out of the language. Cannot run forever. All right, now we allow the other more subtle case. This time the machine can accept, and certainly it can also reject, halt in either case, but it's allowed to run forever as well. That machine is not always halting. Sometimes it can go into an infinite loop. So you have to ask yourself, when it goes into an infinite loop, should you bundle those cases along with acceptances or rejections? And the more sensible answer is, well, it goes into the infinite loop, so it never stops and reports an answer, much less a positive answer. So it can't be an accept, so by default, we'll call that a rejection. So if it goes into an infinite loop, it certainly did not accept. And so it did whatever it is the opposite of accepting, which is rejecting, even though it didn't do it explicitly, it did it implicitly by running forever. It's like one of your friends ignoring you, giving you the cold shoulder. I'm sure most of us have experienced the cold shoulder, the dreaded cold shoulder at one point or another, and they're not responding. So you say, you want to do this, and not saying yes, they're not saying no, they're not saying anything. But them not saying anything is definitely not a yes. So you have to take that as a no. Even though a no was never given to you, you have to assume it is a no. How many get that? Everybody experienced that in their lives. Okay, that's exactly what this machine model here is doing. An infinite loop, no answer, the cold shoulder, is a no or a rejection implicitly. It's certainly not an acceptance or a yes. It was a question, yeah. Arbitrarily looping forever is going forever. He's asking, how does a machine determine if it's going forever? It's not the machine that determines whether it's going forever. The machine is either going forever or not going forever. There's no middle ground. There's no going halfway to forever. Think about it, right? There's no middle room in the infinite hotel. So the machine is either running forever or not running forever. And it's not the machine that determines whether it runs forever or not. It just does or doesn't. It's us that determine that. And we don't even have to determine that. We say, if it runs forever, then the machine is of this kind. If it doesn't run forever, its language is of that kind. Or the string is in or out of the language, whether it runs forever or not. We don't have to determine it. It just is. It's a definition. So if I say, if a number doesn't divide by anything less than itself, it's a prime number. If it divides by something less than itself, it's a composite number. It's not prime. So then I say, okay, well, what about a Google -9? Is a Google -9 prime or not? Well, you can say, well, let me see. But I'm not interested in whether a Google -9 is prime. I'm interested in whether it is either prime or composite or something else altogether. And it's not something else altogether. The number is either prime or not prime, regardless of whether we know it is prime or not prime. So how many here know whether Google -9 is prime? Nobody's raising their hand. How many say for sure it's either prime or composite? Okay, everybody's saying yes. Okay, that's the point. So it's not that you have to determine whether it's prime or composite. It's either prime or composite by definition. That's what we're saying here. So a language is either decidable or not decidable. A machine either runs forever or doesn't run forever. There's a law of the excluded middle here. There's nothing other than prime or composite for integers. There's no third state that an integer could fall into or category that's neither prime nor composite but something else altogether. There's a mutually exclusive, exhaustive law of the excluded middle pair of cases. So either it runs forever or it doesn't. But running forever, we equate it with a rejection because it's certainly not an acceptance. It's the cold shoulder. All right. So then if a language recognizes a bunch of strings in a way that allows it to either reject them explicitly or implicitly cold shoulder reject them by running forever, that language is said to be Turing recognizable or just recognizable for short. Okay. So for example, let's say you have a language, here's sigma star, all possible strings, and here's what the machine does on those strings. A, it accepts. B, it rejects. AA accepts. AB, it runs forever on. Never mind why, it just does. I'm telling you it does. BA, it rejects explicitly by stopping. BB, it runs forever. AAA accepts. This one runs forever, reject, 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 run forever, reject, accept. The language of this machine is what? Just from looking at the ones that it accepted. Say it loud. What's the language of this machine? Just by looking at these green ones that it actually accepted. No big mystery, just generalize those 4 green ones to whatever else you think will happen. Any number of A's, it's A star. So A star is therefore a recognizable language, or a Turing recognizable language. It also happens to be a regular language, don't get me wrong, but it's also by definition a Turing recognizable language because there's an algorithm that recognizes it. So that's what that definition is. Okay. So decidable, sometimes I'll say Turing decidable, sometimes I'll say decidable, recognizable, Turing recognizable, same thing. It saves us the trouble of sticking the name Turing everywhere, even though it's a well-deserved honor for him. Yeah. How do you know it runs forever? You don't have to know, it just does. How do you know that a Google -9 is either composite or prime? Do you know that it's prime? No, but you know that it's either composite or prime. That's what we're saying here. It either runs forever or it doesn't run forever, whatever it does. So a Google -9 is either prime or not prime. It's one of the two things. Whichever it is, that's what it is. We don't have to know what it is. Do you know if a Google -9 is prime? No. But you know it's either prime or not prime. That's what we're saying here. It either runs forever or it doesn't run forever. You don't have to know whether it does. You just know that it does one or the other. And all the strings that it doesn't run forever on, and all the strings that it stops on and says yes, those are the language of that machine, and that language is recognizable. It's a definition. Does that make sense? Yeah. He's saying, give an example of a language that's not Turing recognizable. The complement of the halting problem is one. Good question, short answer. We haven't proven that yet, but we will. Very shortly, actually. Probably in the next lecture. All right. And by the way, I can give you not just one example, but an infinity of examples. And not just a countable infinity of examples, but an uncountable infinity of examples. That's how many unrecognizable languages there are. The set of recognizable languages or countable, or the set of recognizable languages or decidable languages is countable because they correspond to Turing machines that do or don't do certain things. There's only a countable number of Turing machines, therefore only a countable number of decidable languages or recognizable languages. But the total set of languages, 2 to the sigma star, the power set of sigma star, is uncountable. So therefore, most of them are necessarily undecidable and also unrecognizable. And in fact, undescribable finitely on top of that. That's a pretty broad, bold statement to make. That most languages, we can't even, not only we can't decide them, not only we can't recognize them, we can't even define them or describe them unambiguously. Because there's only a countable number of descriptions. A description is a finite string, whether it's in English or a formula or whatever, or a Turing machine or a piece of code. There's only a countable number of them. One word. Why is there only a countable number of descriptions, or a countable number of Turing machines, or a countable number of finite automata, or a countable number of push-down automata? Why are all these sets countable in cardinality, not uncountable? Give me a couple of words that says that are within one word. Dovetailing. Now, somebody explain that in a sentence, just so you don't get the idea that whenever I ask you a question and ask you to say one word, if you say dovetailing, you'll be right 2/3 of the time, which is actually true. I mean, that's how powerful this technique is. It covers so much ground, that just like in mathematics, if somebody asks you, what's the value of this thing, if you say it's either 0, 1, pi, e, or square root of 2, you'll be right about half the time. I mean, roughly speaking. So expand that dovetailing word into a whole sentence. Why is a set of Turing machines countable? Yes. How would you map Turing machines to natural numbers? Correct? He says you can. Somebody do it. Other than him. How would you number all the Turing machines? With natural numbers. 1, 2, 3, 4. Just like those guys in prison that say, joke number 37, ha ha ha, everybody laughs. They mapped all the jokes to numbers. Maybe it's not so funny, but. It's a good try, saying do it by tape length. What else? Because there'll be arbitrarily long ones, and in fact an infinite number of ones that accept a one-string language. Think about it. You can accept a string hello world, and then the next million statements will be a C compiler. Won't do much, but it'll accept only one string. You see what I'm saying? So you can have arbitrarily long pieces of code that accept only one string. Another program will accept the string goodbye, and then have the entire operating system of Windows 10 following that doesn't even get called, it's just there. Very, very long piece of code that just accepts the single word goodbye, or prints the single word goodbye, and this language is one string, but it's a very, very long program. There's even longer programs than that. If you try to list them all and then go to 2 strings, you're trying to put guests beyond the last room of an infinite hotel. Okay, so there's another issue here, is that how do you know it only accepts one string, and which is the first and the second and the third Turing machine accept only one string? Because that's an undecidable question. Whether a Turing machine accepts one string or more than one string, that's undecidable in itself. Let's back up from all this. Give you a much simpler scheme. In fact, let's back up from Turing machines. Why is a set of all programs countable? A set of all C programs or C++ programs or Java programs. Why is that set countable? And I'm telling you that it is by virtue of asking you why. I'm not going to ask you why something is true when it's not true. I'm not going to, I don't want to mislead people or play gotcha with you. So why is a set of programs countable? How would you enumerate all programs? There's lots of ways to do it, but name 7. Yeah, go by length of program, sort them by length. There is definitely a shortest C program. It's called main, paren, brace, 8 characters. Right? And same for C, same for Java, Python, C++, whatever. Then there's a bunch of, maybe several programs of 9 characters, 10 characters. But for every character-bound length, there's only a finite number of programs that are valid C programs, or strings at all for that matter, never mind programs. There's only a finite number of strings of that length or less. Arrange them by length. Get rid of all the non-programs. Then number them, 1, 2, 3, 4, 5. So a set of all programs could be enumerated very, very naturally by length. You don't have to do anything more fancy than that. A program is a Turing machine. A Turing machine is a program. So you can do the same thing for Turing machines. Take all Turing machines, describe them however you want, in English, or list all the set of states and all the transitions of the transition function and the alphabet. It's a finite description between quotes, right? How many get that? The description of a Turing machine is a finite description. Just like the description of a program is a finite description. It's the entire set of characters that represent the code, the source code of that program. Nothing more, nothing less. Same for a Turing machine. Take all descriptions of Turing machines as strings, sort them by length. There's only a finite number of options for every given length. A lot, don't get me wrong, it's a lot. It's exponential for every given length, but a finite number of options, exponential or not. Number them all, 1, 2, 3, 4, 5, all the way down the line. So you're enumerating all Turing machines. So a decidable language has a Turing machine that goes along with it. And because it does, and because you can enumerate all Turing machines, make them one-to-one correspondence with the natural numbers, the set of decidable language is also countable. And so is a set of recognizable languages, countable as well. All right? But every decidable language is also recognizable. That's our first theorem. Why is that? Because allowing to run forever is more general than forcing it to stop in either case. So if this never runs forever, you can always occasionally make it run forever if you want, or not even allow it to run forever, but that's a special case of allowing it to run forever. So therefore, if you say it's recognizable, it may not be decidable, but if it's decidable, it's certainly recognizable, because allowing it to run forever doesn't force it to run forever. It's an option. It's not a requirement. Right? It has the option of running forever and thereby cold shoulder rejecting certain strings, but it doesn't mean it has to exercise that option. And if it doesn't exercise that option, then it's one of these that doesn't run forever. Okay? And so a language that's decidable is also recognizable, but some recognizable languages are not decidable. One is not the same as the other. So first of all, how many understand that every decidable language is also recognizable? If it's decided by a machine that never runs forever, it can also be recognized by a machine that has the option of running forever but doesn't exercise that option. How many get that? Okay, good. So one is a subset of the other. The language is not a subset of the other language. The set of languages is a subset of the other set of languages. Be careful about types. Some people on the exam give me the impression that they think that, a regular language must be, that a subset of a regular language must be regular. It isn't. Right? Think about what level of nesting of braces you're talking about. Right? Okay, but some recognizable languages are not decidable. Give me an example of a recognizable language that's not decidable. You already know it by now. We mentioned it many times. Give me an example of a language that's recognizable but not decidable. In fact, so far, it's probably the only example you know of such a thing, so that's a big hint. And I'm impressed with the same 2 or 3 people who keep answering all my questions. That's wonderful. But I want more people to participate. I don't want to call on people and put them on the spot, so don't force me to do that. So that means some brave soul that's on the fence, say something. Give me an example of a language that's recognizable but not decidable. You can recognize it when you see it. A string comes along, and if it's a yes string, you can algorithmically determine that. If it's a no string, all bets are off. We don't care what you do, just don't be wrong. But you can run forever if you'd like. Just don't say yes, because it ain't a string in your language. Halting problem. How many see the halting problem? How do you recognize yes instances of the halting problem and use one word in your answer? In one word, how do you recognize halting programs? Not decide them, because if it's not halting, I don't care what you say. Just don't be wrong and say yes, because it's not halting for that instance. So if a yes instance comes along that does halt, I want you to say yes for sure. If an instance comes along that doesn't halt, I don't care what you tell me. Just don't lie to me. In one word, what's your algorithm? If you can't use one word, use 2 words or even a whole sentence if you must. But really, I want you to use one word, because that forces you to think about the basic idea of what you're going to do. Execute it. And by that, we don't mean put it up against the wall, and we mean simulate it, just to be sure. Run it. How will running it give you the answer? So the answer is simulation. How will that give you the answer? What will that tell you? It's a yes instant, it halts. How will running it tell you that? Yeah, you're simulating it, you're running it. If it halts, eventually you'll know simply by allowing it to run. And when it does stop running, you will know, and you will report a yes, and you'll be correct. That's your algorithm. How many get that? Okay, good. Now, what if it runs forever? What will this algorithm do? The thing that you're simulating is, once you're running it, it'll run forever. What will your algorithm do? Will it stop and say, no, it's not going to halt? Will it play World of Warcraft? Will it make a phone call to a friend? What will it do? It's not a mysterious question. It'll run forever too. You're plainly simulating it blindly, and if it runs forever, you too will run forever. But that's okay. Now that's allowed. But you're going to run forever. You're not going to stop and say yes, so you won't be wrong. You just won't be right. You will reject that thing implicitly by the cold shoulder because you're running forever too. You're not getting back to me with an answer. You're just obliviously running forever, never returning to me. All I'll hear is silence from you. But you won't be wrongly saying yes, it halted, because you're pedantically simulating it. So the halting problem is recognizable. You can tell yes instances when you see them. If a program halts, you know it. If it doesn't halt, you don't know it, and there's no way to know it because of the proof of Turing that we already been through a few weeks ago, a couple of months ago by now. And that's okay. So it's not decidable by Turing's proof, but it's certainly recognizable. And of course, there's languages that we mentioned are not recognizable even. All right, so the halting problem is recognizable but not decidable. So also decidability is a special case of recognizability because the option of running forever is not a requirement to run forever. So if you're recognized by a machine that's allowed to run forever but doesn't, that means you're being recognized by a machine that never runs forever because it doesn't run forever at its option, and it's an option that it has. Okay, so generally it's easier to recognize than to decide. Recognizing things when you see them is easier than deciding which way it goes in every single instance. And the halting problem is one of those things. All right, so I'm going to skip over this section. Your mileage may vary in some of my cartoons. But an enumerator is a Turing machine for a language that prints out all the strings, and they don't have to be necessarily in order. Okay, so a machine that prints out all the strings in some language separated by $signs means that language is enumeratable. It also means it's recognizable. It turns out we'll have to prove that. The order of enumeration is arbitrary. I'm not saying which ones you have to print first, second, or third. You don't have to do them in lexicographic order or anything like that. But if a language is decidable, it can be enumerated in lexicographic order. And separately, we'll prove that if a language is enumerated in lexicographic order, it can be decided. Here's the idea of these two proofs for these theorems. If it's decidable, there's a machine that always says yes or no. It decides it for sure, yes or no, in finite time, always halts, always gives the right answer. So run the decider on every single string in sigma star. Generate sigma star. That's easy to do. A, B, A, B, A, B, 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 A, and so on. Just generate sigma star in a tight loop. Each one of those strings feed to the decider as a subroutine. The decider will say yes, no, no, yes, yes, no on each and every one of those strings. It'll always say yes or no. The ones that it says yes on, print out. The ones that it says no on, don't print out. Move to the next string. So basically, you're printing the language out in lexicographic order, ordered by size, by the length of the string. So if you have a decider subroutine, you can exploit it into making it an enumerator in lexicographic order. How many get that? By running it on one string at a time. And conversely, if it can be enumerated in lexicographic order, you can also decide it. And the 20-second proof for that is if you have a lexicographic order generator that spits it out, you can convert it into a decider. How? A string comes in the door, run the lexicographic order generator, see if any of the strings that come out of there are the string that comes in the door, and more strings will come out because it's generating it in order. And either that string will come out and then you can say yes, or a larger string will come out, longer in length, and then you'll know it's a no because it's a lexicographic order by length. So if a longer string comes out, you'll know that that shorter string will never come out because they're coming out ordered by size. How many get that? All right, and next time we'll pick up on this exactly. Any last minute questions? Pick up your midterms if you haven't yet. We'll see you next time.